No, there's sound now, hopefully. Yes, okay, there's sound. Okay, good. Hopefully it's not too loud or not too quiet. Um, right, so I had this Google Doc, right? And you guys wrote down some stuff. So we'll just try to cover as much as possible. And I suggest we start from the bottom. So start with week 4, go to week 5, go to week 6, and then look at some of the exams. Um, so there was one question in week 4 about the logic axioms, which I guess kind of was left. Also, funny thing, so apparently the answer sheet that we were given for this question was wrong. So even if you have the answer somewhere written down, it may or may not be correct. So, I mean, we'll just go over it one more time, make sure that everyone has the correct answer. And I need to open this stuff here. Okay, cool. All right, so let's see. Okay. All right. So the question is saying that we have a formula which is phi or psi, right? And then we also have no wait, it's d. Never mind. Sorry. So we have phi and phi or psi, and we want to show that this is semantically equivalent to phi itself. Okay. Also, let me pull out this. Right. So, well, the first thing we do is we want to rewrite this, but then we want to get rid of this part, right? Because then we're left with phi itself only. And so one way we can do this is we can apply the identity rule. And so what the identity rule says is that if we have a phi, then that's the same as phi and true, right? So this is semantically equivalent to phi itself. And so we can rewrite this phi here to this. And then what we're left with is phi and true and phi or psi. Right. And so then we can just apply distributivity to this here. And I wrote this down just for clarity. Also, I think I made it. This is supposed to be an and this is supposed to be an or, right? Yes. Sorry. We're warming up. So this is an and this is an or, right? Okay. Well, so we have the distributivity laws, right? So what distributivity is saying is we have a phi or and then psi and chi. Chi. We can rewrite this, right? We can have like phi or psi and phi or chi. And so if you compare this to this, is the exact opposite. Instead of going from here to here, you go the other way around, right? And so you can rewrite this as phi or true and psi, right? And then it's just a matter of swapping these two. So then what we get is phi or psi and true. And well, we know that psi and true is going to be true, right? So we get phi or true. And does that make sense? Wait, no, we need to flip the sign as well. Whoops. Because with distributivity, the signs flip. So we have or here. We have and here. Wait, that's what I just did. Does that make sense? Oh, yeah. So there's an and here. And so because we have psi or true, that gives us true, and then phi and true, that's exactly the same as phi, right? Okay. Sorry if that was a bit confusing, but hopefully now this makes sense. Just follow these steps. So we have identity here. Then what we do is we use distributivity. And then I'm pretty sure this step is called, this is commutativity. Wait, oh my god, go away. Please no. Okay, and so finally what we have here is just domination, right? Where if we apply the domination rule, we can take away this part and we're left with only phi. Yes? So that's just this exercise here. And so I guess we can get rid of this one, unless there's specific questions. So 3B of exam 2007. Yeah, so the thing is, I have this spreadsheet, right? Which is on Canvas. So I'll clear the spreadsheet and you can add new questions to it if you still want them answered, okay? Because like I have to work with two screens. So it's a little bit awkward to have the chat on one side. Right, okay, cool. So I can read chat now as well, but still, if you have specific questions, please put them in the spreadsheet, okay? All right, so that's it for, I guess, logic axioms, okay? I'll just erase this. You can like take a screenshot or whatever, and else it's probably gonna be in the VOD again. So next we're probably gonna go over OBDDs quickly again, because it's not a lot of work. And then we'll get to the hard stuff, which is like induction and predicate logic. Right. So we have OBDs for week 5, question 5 and 6. Okay. So I'll just go question 5 first. Right. So okay, well, someone's on here. Okay. So we have the variable order x, y, z, right? And so what we want to do is we want to build a reduced OBDD for not x or y, and for z. So, well, first of all, we can just draw the OBDD for this thing here, right? So we have x, and then we have a y and a y here. And then, so this is going to be false, false here, true here, false here, true, true, right? That's how we draw an OBDD. We go with the variable order, and since this does not have a z, we don't need a z at the bottom, right? So we know that if we have x or y, then that's going to be false, right? Because it's going to be true in here and then it's going to be negated. So if we have an x, then we already have a 0 here, a 0 here. And if we have a y, then we also have a 0 here, but we have a 1 here. So that's the OBDD for this formula here, right? But then this is not reduced yet, so if we want to reduce it, then, well, first we're going to apply C1, right? And so with C1, we take all the leaf nodes and we collapse them. Okay. And so then now we can apply the other steps. So we also have step C2, I think it was, where if one node has both edges going to somewhere, we can just remove that node and redirect its incoming edge, right? Which is this one. And so now this is the reduced OBDD for this formula here, right? Because we cannot apply any more steps here. Like there's no nodes we can collapse, there's no nodes we can remove. So just like quickly draw this edge again, right? And then for Z, it's very simple, right? So the reduced OBDD for Z is just gonna be if Z is false, it's a 0, and if it's true, it's gonna be a 1, right? So we have the reduced OBDDs for these two formulas. And then the second part of the question asks us to build an OBDD for the OR of these two from the reduced OBDDs that we drew here. And then, well, we probably need to reduce it again. Okay, let's see. Can I? Oh, there's stuff in the background. Cool. Right. So to draw this, it's basically we take the OR of these two, right? Or we can just draw the whole tree out again. So basically what we get is we have X, we have Y here. Or even better. So we have X, which goes to Y here, and then Y goes to 1 here. This goes to 0 here. This goes to 0 here. But now we need to incorporate Z. So what we're going to get here is this OR Z, and we're going to get this OR Z here, right? So obviously this is going to be Z, because 0 OR Z gives us Z back again. And this is going to be 1, right? And then for Z, we know that this one goes to 0 and this one goes to 1. Yeah, and that should actually give us the reduced OBDD, I'm pretty sure. Let me check. Yeah, that's it. So that's also not very hard, right? No, so for the rules C1, C2, and C3, I suggest you always do C1 first, right? Because C1 you can only do one time, but then C2 and C3 you can do in arbitrary order. It doesn't matter which one you do first. And it may even happen where if you apply C2 and then apply C3, then you may need to apply C2 again afterwards. So yeah, you just keep using them in arbitrary order until you have your reduced OBDD. All right, so that's for question 5b, right? The reduced OBDD here. Then for C, what we need to do is we need to draw exist Y for this reduced OBDD. So this one we don't need anymore. This one we don't need anymore. And so what we're gonna do is Select this one. Okay, no. What part? When do you have 0 and 1? So 0 and 1 are always going to be the leaves, right? The bottom leaves. If that makes sense. Bro, how? Why can I still see the drawings behind? Okay. So if you have a 1, it's like a true value. If you have a 0, it's like a 0 value, right? So we know that if we have like x or y, right? And the order is x, y, then well, we know that this is true if x is true, right? So if x is true, this will always be true. And if x is false and y is true, then this still holds, right? And so that's where the zeros and the ones come from. I hope that makes sense. All right, so yeah, I'll have to redraw the tree because I removed it. So the OBDD that we had was x, y, 1, and then az here, which goes to 1, and this goes to 0. Okay, so this is the reduced OBDD for question 5b. Right. So now what we need to do is we need to write the OBDD for there exists a y such that this statement is true, okay? So what this is saying is there is a y, there is some combination of y, either 1 or 0, right? Because we can only choose between 1 and 0. So there is a y, either 1 or 0, for which this thing holds true, right? And so what we want to do is we want to draw the corresponding tree for this, okay? And so whenever you have a question which looks like this, what you're going to do is you're going to take this variable, right? And you're going to draw both OBDDs for all the values that it can get, okay? So we can assign 1 to y. Well, if we assign 1 to y, we know that we're going to take this edge here, right? And we're never going to take this edge here. And so you have an x here. The y we remove, and we're going to take this edge here, and we're going to redirect the incoming edge for x, okay? And then, well, this still goes as it would normally go. Okay? I hope this makes sense. And so you can see you can apply C2 here, and you can even get rid of this part. And so for y is 1, this is the tree that we end up with. Okay? Yes, you remove the x. And so for y is 0, what we get is we're going to take this edge here, right? So we have an x, which goes all the way to 1 here. And then it goes to z here, and z goes to 1 here, and to 0 here, right? So this is the tree for y is 0. So now we have constructed both trees for variable y. And because we have this sign here, it says there exists, it means that we need to take the disjunction, okay? And so if we have for all, then we take the conjunction of y1 and y0. And so if we want to take the disjunction of these two, that's very simple. So we have x goes to z and goes to 1. Right, so this z we can plug in here, and we can plug it in here, right? So what we get is this becomes z or 1, and this becomes z or z, right? Well, z or z becomes z, and z or 1 becomes 1, and so the tree basically stays the same. So this tree, or this OBDD here, corresponds to this formula. And that's your answer for 5C, okay? Now, in the case where instead of there exists a y, we have for all y, which is what question D asks. Now, instead of taking the disjunction, we take the conjunction, right? And so what we end up with is here we're going to get z and z, and here we're going to get z and 1, okay? And so z and 1 is going to give us z here. And z is still going to give us z here, right? And so, 1 second. We still know that if z is true, it goes to 1. So we get this here and this here, okay? And you can see that these z's are the same, so you can rewrite this as no x at all. We just have a z which goes to 1, goes to 0. And so that's the OBDD corresponding to this formula here. So you don't have to use it for 0 because like this, you have the z above here. So it's so the thing is, you look at the variable ordering, okay? So we have x, we have a z, and we have a 1 and a 0 here, okay? And so if you apply this rule, you apply it to the children of x, okay? And so this is a child of x, and this is a child of x. And so you apply it to its children, and this is not a child of x, so you don't apply it to this one. Yeah, I'll explain again. Right, so we have a 1 here and a 0 here, right? So whenever we do this, okay, we apply this to the children of the node that we're looking at, okay? And so we know that that z is a child, so this is a child of x, right? Because it's connected. And z is also a child of x because it's also connected. And that's where you apply these rules on. So because these are the childs, we're going to have z, and we're going to have z and 1. And that's how you end up with the final answer. Does that make sense? And we don't apply it to this one because, well, this is not a child of x, it's a child of z here. Yes? Cool. Very nice. So then that's question 5 of week 4. Or no, yeah, I think it's week 4. Or week 5. No, it's week 5, yeah. Oh yeah, don't worry. The VOD should be recorded. I mean, the thing is, we have a lot left to do, so I can't spend too much time on everything. But I hope it's clear. Right, so we have question 6 for week 5 still. So what we have is we have a variable order x, y, z again, right? And so we have the formula x and y, or not x and not z, right? And we want to construct a reduced OBDD for this formula. Well, we know that the ordering is XYZ as given by the question, right? And so what we're going to have is an X on the top. We're going to have a Y here, and then Z's here. And now it's just a matter of looking at how this works, right? So we know that if we have X and Y, then it does not really matter what happens here, right? This statement is going to be true if X and Y. So if X and if Y, then this is going to be true in both cases. And so for these two, we can't say yet. Let's see. Well, we can also look at the second statement. So here we have X, but we don't have Y per se, right? So, well, we have not X is false. So this is false already. So these must both be 0. Hopefully that makes sense. So if we have not X, then this is true, but then we also need not Z. And so this is what the tree is going to look like, okay? Yeah, reduction steps are important for the exam. Yes. So first step is C1, right? So have the 0 here, have the 1 here, and then, well, this one's going to go to 1. This one's going to go to 1. These are all going 0. And these are both going to go 1. Right. So, well, first step you could do is you could apply C2 and get rid of this one and this one, right? Because they have both nodes going to the same end node. So what this means is we can remove these two. And now I forgot which one goes where. Okay. So this one we can redirect. And this one we can redirect, okay? And similarly, these two we can collapse, right? Because they have, this one goes false to 1 and this one goes true to 0, both. Right. And so here you have an example where now you can apply C2 again, right? So because we can apply C2 again, we can also get rid of this node here. Redirect this edge. And so this is the final OBDD that we're left with. If your final answer is correct and you don't clearly show C1, C2, C3, I'm not sure if you'll lose too many points, especially because, you know, this is like an online exam, so maybe the teacher is like kind of lazy and he's just going to look at the final answer. But do try to mention the steps because it's preferable still. Okay. So if you have questions I want to do, please refer to the spreadsheet, the Google Docs spreadsheet, because there I'll look at any new questions that pop up. Wait, empty this. All right, so again, they want you to do there exists a x, right? Which I guess we can do. So to construct there exists an x, what we do is we take x0. Well, if x is 0, we're taking this one here, right? And so we're never going to go here. And so what we end up with is C. Why even draw this? Don't need to. Right? So this is the tree for x is 0. No, they're not paying me overtime. But it's fine. It's fine. And so if we have x is 1, then we're going to take this one and we're going to end up with y, right? And so y is going to go 1 here and 0 here. Okay? Now, since we want to make there exist, we need to take the OR of these two, right? Well, we know that the ordering is y to z. So, fuck. Okay. So remember the rules, right? So you go to the children of y, which is 0 and 1, and you take these OR with c. Or c. Well, this is going to be 1. Agree? And this is going to be z. And so we know from c that c goes to 0 here and it goes to 1 here. And so this is the tree, the final OBDD for there exists an x. Okay? Now, if we want to calculate the OBDD for all x, we do the same, right? So we start off by drawing y. And then what we get is 1 and z. And here we get z and 0. Well, we know that 1 and z is going to be z. And z and 0 is going to be 0. And we know from z that this one goes to 1 and this one goes to 0. And so this is the OBDD for all x. Okay? And so that's going to be question 6 for week 5. Then I also had a question about function compositions, which is like sets exercise, sets week 5. So to explain function compositions, I'll just refer to question 6, I guess. So this is week 5 sets question 6, right? And so for question A, we need to give descriptions or formulas for fx, gx of the two functions. So we have a function which is called, actually, wait. Okay, yes, cool. Okay, so we have the question here. Right. Amazing. So we have these functions here, right? We're just given definitions, and we need to give descriptions for these functions. Okay, so what you do is you work from right to left. Why? Because we have these dots in the middle, and these dots, they mean after, right? So it's saying we're squaring after we add, after we multiply by 2. So what you're going to do is you're going to take an x, right? And first you're going to multiply it by 2. Then you're going to add 1 to whatever's left here. And then we're going to square root the whole thing. So this is going to give us the square root of 2x plus 1. Okay? So that's the answer. It's super easy. And so for the second one, you're going to start off with an x. You're going to multiply by 5. Okay? You're going to take the inverse of the square root. Okay? So that's the same as squaring. And then you're going to add 2 inverse, so minus 2. And I'm going to double check if that's the correct answer, but I think it is. Yeah, sure. That's the correct answer. Cool. So yeah, that's for G. And this is for F. Right. Okay. So that's the first part. And now in the second part, we want to consider the inverse functions of the functions f and g below, and we want to give descriptions of the inverse functions. So we want to take this function here, we want to inverse it, and then we want to write down a description. Okay. So, well, the inverse of multiplying by 5, which is already inversed, so that's just going to be multiply 5, right? Also, to better explain it even, so this is what it's originally what it originally is, right? So if we want to inverse this, we're gonna inverse the order in which we perform the steps, but we're also gonna inverse the steps themselves. Okay, so f inverse is gonna be multiply 3 inverse, add 2 inverse, multiply 5 inverse, but it's already inverse, so that becomes normal multiply 5, right? And so what we get is 5x minus 2, and then this whole thing times this whole thing divided by 3. Okay. And so for g, well, g is given by the square root inverse after add 1, right? So if we want to create g inverse, then what we do is we get add 1 inverse after squaring, and so we apply the square root, and then we do minus 1. And that's the answer for G. No, don't collaborate, guys. Don't come. Right, so I hope that makes sense for function compositions. And I guess that finishes all the information from past weeks, and I guess we'll just go to the information for this week. which is going to be on predicate logic, as well as induction, that kind of stuff. So I guess I'll start with logic, week 6. And then we'll just go to question 4. All right, so ignore the black line, but this is the question. Question 4 for week 6 for logic. So we have a model consisting of the set elements A, B, C together with unary predicate D and a binary predicate E defined by this set here. Okay. And so what we want to say is whether or not any of these here hold or do not hold. And so for the first one, you can see that it holds, because what this is saying is for all values of x, okay, for all values of x, there is some y in which exy works, okay? And that's true because all x that we can have x is a, we can have x is b, and we can have x is c. Well, if x is a, then we have EAA. If x is b, then we have EBC. And if x is c, then we have ECA, right? So for every case in which x is a, b, or c, there's some y that also works. Okay, you can see up there. Can you see now? Yes, cool. Right. So you guys see, right? So this is an example in which the first one works, this one, and this one. Okay? So this is why the first one holds. Actually, like this. Okay. So the second one also holds because this is saying that there is some x, there exists an x for which all y work. And well, you can see that for A, all y work, right? We have AA, AB, and AC. So for this x, there's some y that we can, there's all y's we can relate. There's an x for which we can relate all y's. That's basically what this is saying. So therefore this also holds. Now the third one does not hold, and it does not hold because it's saying that for all x and for all y, we have xy or yx. And so that's saying that for all xy combinations, it works one or the other way. But you can already see that arbitrarily EBB, for example, does not exist, right? And similarly, ECC does not exist. So if we take B for x and for y, then, well, it does not work. So not for all x and not for all y does this statement hold, and therefore it's false. Okay, so C is saying that for all x and all y, right, for all xy combinations, we have EXY or we have EYX, okay? So let's say we take x is A and y is A, okay? Then we have AA, so that works, right? Now let's say this is not A, but this is B, then it still works. If it's C, it also works, right? Now if this is B, well, we can't make y is A, right? Because BA does not exist, only BC exists. BB also does not exist, so we can also not put B in here. And so because it does not work for all values of y, this part of the statement is false, right? There's not, for every x, there's not all y's that work. That's basically the idea behind C. Cool. Right, so D also holds. Well, it holds, so I don't think it's too relevant to explain why. And F also holds, but then E does not hold, and so I'll explain why E does not hold. Okay, so E does not hold because E is saying that for all x, right? For all x, so there may be A, B, and C. It's saying that for all x, we have that for all y, if there is xy, then there's also dx, okay? So now let's say we take B as x, okay? If we take B as x, then the only y that we can choose is C, right? Because C is the only combination of xy that we can have with BC, right? And so if we have BC here, then that implies that we also have D of B, which we do, it exists. Okay, we have lag or something. Right, and so similarly for C, well, the only combination for C that we can make is C with A, right? And so it implies that if CA, then we also have DC. Which in fact also exists up here, right? So that also works. But now this is where we have a problem. So let's say x, we take x as A, right? So then for all y, where this holds, there exists a d of x. So, well, this implies that there's also a d of A, which, well, there is no d of A, right? And so, because this does not exist, that's why this one fails. So yeah, this stuff is a bit annoying, but it's a matter of just reading what it says and then looking at the model that you're given and see if it fits in the model. And so if you can find one contradiction, then depending on what the sign is saying, it may or may not be true. Second to last one again. Okay, sure. Right. Right. So the second to last one is saying that for all x, right? For all x, we have that for all y, if there is an xy, then there's also a d of x. Okay? Well, we know that for x is b or x is c, there is a bc and there's a ca, right? So this implies that for x is b and x is c, there must also be a d of x, which there is. There's a db and there's a dc. So it works for x is bc. But if we say x is a, well, then we have 3 xy combinations which work, and so this implies that there's also a d of a. But there's no d of a, it does not exist. And because this d of a does not exist, this whole statement fails. Well, d holds, so there's not much explaining for d. It just holds. Why does it hold? Because what d is saying that for all x, we either have d of x or we have e of xx. Well, we know that for x is a, we have e of aa, right? It exists here. We know that for x is b, we have d of b. And we know that for c, we have d of c. And so this statement holds for all x, right? For all x, there's a valid outcome. Okay, and then we have question 5 as well. And I guess for 5 we'll do a few. Well, the thing is, on the exam, so what this question asks is, let me pull up the question specifically. So what the question says is, say for each of the following formulas whether they hold for the model, okay? If they hold, you just say they hold, right? And if they don't hold, you provide the counterexample for which it does not hold. Yes? Does that make sense? That's literally what you do. If it holds, it holds. If it doesn't hold, you give a counterexample. So question 5. Right, so this is question 5. I'm gonna go through it a little bit fast in a sense that everything which is equivalent I'm just gonna give you and not really go over it because there's no point. So B is equivalent. Wait, actually, okay, so this one's equivalent, C is equivalent, and E is equivalent. So we have 3 formulas which are not equivalent, okay? And F is kind of stupid, so we're gonna skip F and we're gonna just discuss A and D, okay? Don't bother with F. I don't think you're gonna get anything as complicated as this on the exam. So, well, so what the first one is saying that for all x, we have cx or dx, okay? And so cx or dx is just saying something about an object, right? A model is just a description of what your universe may look like. So let's say we have a function r of x, okay? And r of x is saying that x is a red object, okay? And so this may be our model. Our model may be something like r of a and b, okay, with elements a, b. So what is this model saying? It's saying we have 2 objects, a and b, but only object a is red. Okay. So now what we do is instead of rx, we have c of x and we have d of x. And so what the first one is saying, this one here, it's saying that for all x, x is either c or d. Okay? Whereas this one is saying that for all x, they're all c, or for all x, they're all d, right? So now consider if this is our set AB, right? Well, we can write that C of A and D of B. Now, if this is our model, then the first statement holds, right? All x are either C or D. But the second statement doesn't hold because not all x are C and not all x are D, right? So this holds for the first one, but it fails for the second one. And that's why they are not equivalent, right? We found a model in which one holds but the other doesn't. If they're equivalent, then no matter what model we make, both of them will either hold or not hold. So it's the same as truth tables, I guess, in a sense. If the truth tables are the same for a formula, then the formula is equivalent. If they have different truth tables, then they are different. And so it's the same with models and predicate logic here, okay? Now, the second part of the question is asking whether or not one formula entails the other. And so this formula here, the second one, entails the first one. Why? Because if all elements are C, then still for all elements they are either C or D, right? And if all elements are D, then still for all elements they are either C or D, right? I hope that makes sense. So that's how you would kind of explain this. So for A, so if we zoom in on A, it's saying that for all x, right? So these are our x. These are all the x we have. We have A, B, so we only have two x's, right? For all x's, they're either C or D. It doesn't matter, but like, so CA and DB, this is a valid model for the first one, but CA, DA is also valid, right? Because for all x, AB, they are either C or D, right? But then this doesn't hold for the second one anymore because the second statement, this part, is saying that for all x, we only have C's, or for all x, we only have D's, right? Which is not the case here. Well, we do have that all x are C or D, but, well, clearly not all x are C because we have a D here, and not all x are D because we have a C here, right? And so you know that if this statement holds, this statement also holds by default. And so therefore this one, this formula here, entails this formula here. Because if this one is true, the other one will always be true, but it does not work the other way around. And I hope that explains it a bit. So that's how you approach predicate logic. And then we also have D, which I guess we can also do. So if you only have CA and DA, then it holds for the second one, yes. Then the second one holds, and then the first one also holds, obviously, yes. Then they both hold. If this is the case, then both of them hold. But we have given a counterexample in which the first one holds, but the second one doesn't, and so therefore they're not equivalent. E is equivalent. So you're saying if we have an element, we have a model AB, and so we have PA and QB. This holds for the second, but not for the first one. Well, the thing is, we're talking about exists here. So it doesn't have to hold in all cases. It may hold in some cases. So this may not hold, but then if we swap them, right? Let's say we make this B and this B, then it does hold, right? Plus, you can't have different x's here. You can only have one the same x. So yeah, so the thing is, you can have multiple models, but the main takeaway for this question is two formulas or like two predicates are semantically equivalent if and only if they hold in all the same models, right? If a model holds for the first one, then the model also holds for the second one if they are semantically equivalent. If they are not equivalent, then we can find some model in which one holds but the other does not. And so I'll just go to question D and I'll show you another example. Well, so D has existential quantifier, so we'll just go to this one and we'll see how it works out, right? So we can consider the set AB. And so assume the relationship AA and the relationship AB, right? So it's saying that for some x, all y work, okay? So here what we do is we say x is A, okay? And then so for all our y, the relationship must hold, okay? So we have our xy, which is like xy here, xy here. And then for the second one, it's saying that there's an x for which all y, the opposites holds. So that's saying that there exists an x, A, for which AA, but also BA, right? And so clearly these two are not the same, right? AB is not the same as BA. And so since these two are different, right? So like the first model only holds in these two cases and the second model only holds in these two cases for x is A, right? And so we've shown that in one of the cases, namely this one, they do not correspond. And therefore they are not semantically equivalent. And it also works the other way around. And also because it works in both ways, the left one does not entail the other one, and the right one does not entail the left one. No, you can't make up stuff. Well, so the thing is, you can make up stuff to make one model work, but you can't make up stuff such that both models work at the same time. In all cases. There may be a case in which both models work, right? But there will always also be a case in which not both of them work at the same time. And that's this case that we've shown here. And because we found one case in which they are not equivalent, well, that's enough reason to say that the formulas are not equivalent, right? It's like, well, yeah, we built two truth tables, but there's one row in which they're not equivalent. Well, that means that the truth tables are not equivalent, right? Right. So if this is still confusing, there's going to be more predicate stuff for the later exams that if we have time, we can still discuss. So don't worry yet. I'll just go to sets week 6, which is going to be induction, which is completely awful. But yeah, we'll see. Yeah, exactly. So what you do is you need to find a model in which they are not equivalent, and if such a model does not exist, then they are equivalent, right? It's the same as you have two formulas, you need to construct a truth table for both formulas, and if all rows are the same, if you cannot find a row in which they differentiate, well, then they are the same, right? They're equivalent. So yes, you're right. If they're equivalent, then you say they're equivalent, yes. Literally. That's literally it. And if they're not equivalent, then you give a counterexample. All right, so induction. Mind you, this is the one question I completely screwed up on the exam last year. So I'm not sure if I'm the place you should be to learn about induction, but I did become better at it, so I can still try to explain, and I guess it'll make more sense. So what we need to do is we need to calculate the terms t2, t3, t4, t5 of the sequence. We know that t1 is 2, right? And so this is just plug and play, right? So we have like a formula, which is tn plus 1 is 2 tn minus 2n plus 3, right? So let's say we want to calculate t of 2. Well, we know that the t of 2 is going to be t of 1 plus 1, right? So if n plus 1 is 2, then we know that n is 1. And so then what we get is 2 times t of 1 minus 2 times 1 plus 3. Okay? Yeah, the FUD will be public. And like, even if it's not public, I'll just download it and I'll upload it on Canvas or something. Well, induction is kind of chill, and I don't think the stuff on the exam will be super hard, but if you don't understand induction, even the easiest question will become hard. Okay? So anyway, to calculate T2, what you just do is you plug in the previous formula, right? So, well, we know that T of 2 is 2 times T of 1. T of 1 is 2, so that's 2 times 2 minus 2 times 1 plus 3. So that's 4 minus 2 plus 3. So that's 5. Okay? And that's the answer for T of 2. So now if you want to calculate T of 3, right, then, well, we have then n becomes 2. Two times 2, right? So that's 2 times 5 minus 4 plus 3. So that's 10 minus 4, 6 plus 3 is 9, is T of 3, right? So I hope this makes sense to everyone, right? Because this is like super easy. This is just plugging in all the numbers and, you know, coming up with your answer. This is not the hard part. Okay? So hopefully no questions about this. And if there are, well, you got the answer sheet, so you can look on the answer sheet. But then the induction part is annoying, right? So for the induction part, every induction question will look something like a t of n plus 1 function and a t of n function, okay? And there will always also be a base case, which is this one here, okay? So it's important you figure out which is which. So now, what you want to do first with induction, you want to prove your base case, okay? Prove base case. And so we know that our base case is t of 1, right? And so we plug in t of 1 in here, right? So that's 2 to the power 1 minus 1 plus 2 times 1 minus 1. So that's 2 to the power 0 plus 2 minus 1. So that's 1 plus 2 minus 1 is 2, right? And that's what it says here. And so therefore the base case has been proven. Okay? So we've proven the base case, and that's the first thing you do. Now, after you've proven the base case, you want to prove that if t of n holds, then t of n plus 1 also holds, okay? And so if we rewrite this as t of tn of 1, t of n plus 1, then what we get is 2 to the power n plus 1 minus 1 plus 2 n plus 1 minus 1. And so this is basically the answer that we want to find, okay? So, well, first thing you do is you need to prove by mathematical induction that for all n bigger or equal than 1, it holds, right? So instead of working with an n, what they usually do is they work with a different variable, okay? Because we're trying to do a proof here. So assume that there is some m bigger or equal than 1. Then what we get is t of m plus 1, right? So as soon as you choose your m, what you're going to do is you're going to take this formula here, and you're going to substitute it in the formula on top here, okay? And so t of m plus 1 is going to be 2 times 2n minus 1 plus 2n minus 1 minus 2n plus 3, okay? So what we do is we take this formula and substitute it into the formula on top here. Right, and so then what we do is we figure out what this is supposed to be. So also this is an m, not an n. Right, so this gives us 2 to the power 1 times 2 to the power m minus 1 plus 4m minus 2 minus 2m plus 3. Right, so this is the answer that we get, right? And so the thing is, this part we can rewrite so you can rewrite this as 2 times m plus 1 minus 1. Okay? And so now if you look at this part of the formula, this is the same as this, except that on the places of n, we now have m plus 1. Right? And so that's basically your proof. That's literally what you have to do. So now what you can say is that, well, if t of m holds, then that implies that t of m plus 1 also holds. And that's the proof. You mean this part? Right. So the way you get to this part is once you've proven your base case, okay? Once you've proven your base case, what you do is you assume, instead of working with n, you assume, well, now we have some m, which is bigger or equal than 1, right? Because that's the constraint that we're given. Okay? So we assume some m. Once we've assumed some m, what we're going to do is we're going to take this formula here, this t of n, and substitute it into this formula on top here. Okay? So you substitute this one into this one. And once you've done this, you end up with this here. And when you simplify this whole thing, you end up with this here. And this, by chance, is actually t of n plus 1. That's this formula here. But instead of n, you have n plus 1. It's a bit complicated, but there's more exercises on this. So I'll just go to the next exercise, see if it makes a bit more sense. Because it's a repeating pattern. You do the same every time. So we have question 4. Right, so so the first thing you do is prove the base case, right? So, well, the base case n is bigger than or equal to 1, so the base case is n is 1, because that's the lowest n that we can choose, right? And, well, in the case where n is 1, then what we have is 1 over 1 times 1 plus 1. Right, and so we know that both of these are 1 over 2, right? And so therefore the base case holds. It's just plugging in n into this formula here, right? So we know the base case holds. Now, since we've proven the base case, what we do now is we assume some m, some arbitrary m bigger than or equal to 1, because that's the constraint that we have set here, right? And what we're going to say is that, well, if m holds for this here, then it must also hold for m plus 1, which is what we want to prove here, right? And so now this is a bit trickier, because this part of the formula you can rewrite as this here, right? And so then if you rewrite this as m plus 1, or like this whole thing can be summarized as this here. So if you want to rewrite this part as m plus 1, then what you get is n over n plus 1, right? So that's this whole thing here, plus m plus 1 times m plus 1 plus 1, right? Because this last term, this one here, right? If we calculate this formula for m plus 1, then that's everything up until n here, plus n plus 1, right? So there's another term that comes after this here, which is the one for m plus 1. And so that's this term that we've added after it. Okay? So that's the logic behind it. And so once you've done this, well, now you're just going to write this out, right? So, well, what we can do is we can multiply both of these by m plus 1 plus 1. So you get m times m plus 1 plus 1. And then because both terms are the same, we can add this one to the left side, right? So then what we get is this. And so what we can do here is we can take this one here and take it outside, multiply it by m, right? And then finally we can rewrite this as m plus 1 over m plus 1 plus 1, because we can divide by this here, right? And so if we divide this by this, we end up with m, and if we divide this by this, we end up with 1, right? So this is the final formula that we end up with. And well, if you compare this part to this part here, they're exactly the same, right? Except here, instead of n, we have m plus 1, and here, instead of m plus 1, we have m plus 1 plus 1, right? And so this is saying, so basically what you've shown here, so just this part alone here, if you have this as your final answer, then now what you can say is that if, well, your formula T of m holds, then that implies that T of m plus 1 also holds. And I still know that's confusing. But so the idea is prove the base case, okay? Substitute your n into your n plus 1, then calculate the answer. And once you get the answer, then compare it to your original n and see if they are the same, right? So I guess because of time, I'm gonna skip 4b, okay? And then if I skip 4b, I can move on to question 5. Right, so for question 5, we have to prove for each of the following statements by we have to prove each of the statements by mathematical induction in n, okay? And so we say that for all n bigger or equal than 4, we have that n squared is smaller or equal to 2 to the power n, okay? Well, the base case n is 4, we can prove, right? So we have that 4 squared. This holds, right? Because this is basically saying 16 smaller or equal than 16, right? So base case holds. That's simple, I guess. But then now the inductive step. So for the inductive step, what we say is we take an arbitrary m bigger or equal than 4, right? Because that's the constraint that we have, right? And so we want to figure out what this becomes if we go to m plus 1. Okay? Well, if we write this out, then what do we get? Well, we get m squared plus 2m plus 1, right? And so because we have this statement here, because we know that n squared is smaller than or equal to 2n, that means that if we replace this m squared with 2 to the power m plus 2m plus 1, whatever's on this side is always going to be bigger or equal than whatever's on this side, right? Yeah, there's still a bit of predicate stuff left on the final exams, so I'll get to that as well. No, so what I suggest is after I finish this one, 5, I'm going to do question 6, which is going to be on transitive closure, okay? And then maybe there's time left for question 7, and then there's going to be an induction question on the exam of 2019, the one which I did last year, the one which I completely screwed up. But looking at it this year again, it actually makes a lot of sense, and it's not that hard. Okay? So anyway, now we've proven this part of the side, right? And so now what we also want to do is we want to show that what happens if we have 2m plus 1 here, right? Okay. So now because we want to show this, well, what do we get here? We get 2 to the power, that's 2 to the power 1 times 2 to the power m, right? That's the same. So that's the same as saying 2 times 2m. And well, that's the same as saying 2m plus 2m. Which is the same as 2m plus m times m. Right, so it's just writing on this stuff. And so since we know that this is always bigger than this, we know that this is always smaller than what's on this side, right? But then also we assumed m is bigger than or equal to 4. right? Actually, wait, remove this part. This still holds, right? Because m is bigger than or equal to 4. So 4 is the lowest number that we can have here for m. So there cannot, these m's are also both going to be 4 or lower, right? So then this statement still holds like this. And so if you take this statement and this statement and now put them next to each other, right? Then what you get is 2 of m right? And so basically you can kind of ignore the middle part, but it's still showing that this is smaller or equal than this, which is exactly like these two, but then with m plus 1. And that's kind of the idea for this question. Which, I mean, so this is m plus 1 squared, and this is 2 to the power m plus 1. Right. So this middle part here is just rewriting this stuff here, for example. So 2 to the power m plus 4 times m, that's the same as 2 to the power m plus 2m plus 2m, right? Agree? Because, well, this is 4m and this is also 4m. So if this stuff is confusing, well, I guess just re-look at the answer sheet that you guys were given, because it's basically a kind of a rewrite of it, but then with a bit more intermediate steps, I guess. I guess I'll just go to transitive closure, because there's actually some stuff to explain about transitive closure, though. Right. So with transitive closure, what you want to do is you want to draw all the transitive arrows that are currently not present. Okay? So what you'll do is you take all your nodes in your graph, A, B, C, D, E, and you look at each of them separately, and you look at all the arrows that they may be missing. So A cannot reach any other node, so there's no arrows we need to add. We know that B can reach C, but B can also reach E, it can also reach D, and it can also reach A. And these arrows, D, B, D, B, E, and B, A, they don't exist, right? So we need to add them. And similarly for C, well, C can reach E, C can reach A, and C can reach D, and it can also reach itself. And so these arrows we also need to add because they don't exist in the graph. And for D, we know that D can reach C, D can reach E, D can reach A, and D can reach itself. So we have D, E, and A, right? And so finally for E, we know that E can reach A, which it has, it can reach D, it can reach C, which it doesn't have yet, and it can also reach itself. B can also, yeah, it can reach C, but it already has this arrow, so we don't really care. The arrow already exists. So these arrows that I've drawn here, this group, are all transitive arrows, so you can't see them yet. And so now we're going to add these transitive arrows. So we have B to C, C to E. Right, so this is the original graph, right? So now we add the transitive arrows, so we have B to D. we have B to E, and we have B to A. Then we have C to C. We have C to D. And we have C to A. Then we have D to D, D to E, and D to A. And finally we have E to C, and we have E to E. Right, so that's transitive closure. We've just looked at all the transitive arrows that we're missing, and we've added them, and that's what transitive closure basically means. Yeah. Well, a transitive arrow means that if we can go from B to C and from C to E, then we can also go from B to E directly, right? That's what a transitive arrow is. And so because B to E didn't exist, well, B to E is still transitive, so this arrow we need to add if we want to give the transitive closure of this graph. Yeah, but so the thing is, transitivity in itself is transitive, I guess, if that makes sense. So if like A to B and B to C and C to D, well, then still A to D is still possible, right? So it doesn't really matter how many steps. Transitivity goes over infinitely many steps. The reason why it's explained with 2 steps is because it's easier to explain. Well, because we can go from C to E and from E to D and from D to C, so we can go from C to itself again. And that's 1, 2, 3 steps, but it still counts because it's still transitive. Okay? Right, so question 7, I'll just go over A quickly because it's not really a super relevant question. But I still just want to discuss it, just, so you can see how transitive closure may occur differently, I guess. So we have the relation R in N with description is a direct predecessor of, that is the relation R. So R xry implies that x plus 1 is y. And we want to give the transitive closure of this, okay? And so what it means is that, so what the relation describes is that, let's say we have these numbers here. Well, this is saying that if x is 1, then x is related to 2, right? And 2 is related to 3, and 3 is related to 4, and so forth, right? And this keeps going. But then if 1 is related to 2 and 2 is related to 3, then this relationship also exists, right? And this one also, and so forth, right? So any number is related to all the numbers that are above it. That's basically what this relationship is saying. And so now the only thing that we need to do is convey this into words, right? And so to convey this into words, what we could say is that the transitive closure of R, right? Yes. So the transitive closure of R is basically this. It's this sign, right? So for all xy, we have that x is smaller than y. So as long as y is bigger than x, then x relates to y. That's basically what this statement is saying. Okay, and that gives you the transitive closure for this relationship here. So for any x in this relationship, we know that it relates to all y that are bigger than it. Okay? So that kind of sums up all the exercises that we've had for, I guess, the weekly exercise stuff. Logic 6. Okay, so the last exercise of Logic 6 we already did. So, just to rewatch the VOD, I guess. But Logic 6, question 3 I can still do, and then after we've done that one, I'll just move on to the final exams, okay? Because the final exams are going to be the most relevant for you guys anyway. Right. So for question 3, I'm definitely not gonna do E because E is stupid. I think I probably made a typo. I probably meant to write down m squared, and then it is m times m. So probably made a typo there. Sorry. Okay, well, so to go to this question for the predicates, so we have to translate the following phrase into predicate logic, okay? And so what we can do is we can take an element and apply S to it, and then it's a student. We can apply L to it, and it's a lecture. And we can also apply A to 2 elements, and then X attends Y, okay? Right. So what the first relationship, or what the first predicate is saying is that no student attended every lecture, okay? One second. So if you think about it, what this is actually saying is that for all students, right? All students, there's not a single student which attended every lecture. So naturally, what you want to do is you want to start off with for all x, where x is a student, okay? So we're saying for all x, where x are students, so for all students, right? For all students, well, if they didn't attend every lecture, that means that for every student, there's one lecture which they did not attend, right? So for every student, there exists a y such that, well, y is a lecture, right? And also, the student x did not attend y, which is the lecture. Right? And so that's going to be the answer for the first one. So we can translate this into this. So what it's saying is for all x, for all elements x, if x is a student, well, then there must be an element y such that y is a lecture and the student did not attend this lecture. So it's saying for all students, there's at least one lecture which they did not attend, which is basically what this sentence is saying. And so for the second one, no lecture was attended by every student. Well, that's saying that for all lectures, there is at least one student which was not there, right? So for every lecture, there's at least one student missing. That's what this one is saying. So it's basically taking the first one and flipping it, right? If that makes sense. So for all lectures, there exists an X such that X is a student and they did not attend the lecture, right? So that's the second one in predicate logic. And so then the third one, each lecture was attended by some student, right? So, well, you see each lecture in the beginning, so you know that it's going to look like something like this. For all lectures, right? There exists some X, such that X is a student, right? And they attended the lecture. So as you can see, C is the opposite of B, right? They're exactly the same except for the last statement, where here it's saying that for every lecture there was one student that didn't attend, and this one is saying for every lecture there was a student that attended. Okay. And then, well, D is kind of a mess, but I guess we'll still do it. Right, so for each pair of lectures, some student attended both lectures. Okay, so because we want to, so we have each here, so we know we're gonna have something with this sign, but it's a pair of lectures, so we're gonna have some Y, and we're also gonna have some Z, right? So this is a pair of lectures. Logic exercise 4, question 7. Don't bother, okay? Like, you're not gonna get anything like that complex on the exam, and it's super annoying. It's gonna take a long time to explain that one, so it won't be worth your time. Like, if you can solve the first 6 ones, you're gonna be fine. You're gonna be able to do everything on the exam. So for each pair of lectures, some student attended both lectures. So for each pair of lectures, for all Y and all Z, where, well, both of them have to be lectures, right? Y is a lecture and Z is a lecture, right? For every pair of lectures, wait, we need one more. For every pair of lectures, there exists some student, right? Some student attend both lectures. So for every pair of lectures, there exists a student which attended both, right? So this X is a student, and X attended Y, and X also attended Z. Well, I don't know how many brackets, but you get the idea. So what it's saying is for every pair of lectures, for every pair of YC, if both of them are lectures, no, you don't have to say that they're not equal, because so they can't be equal because you select 2 different elements here. You can't put both. You can't put the same element here. They have to be different. And so for every pair of lectures, there exists a student which attended both of them. So yeah, pretty straightforward. And then the last one, well, you got the answer sheet, so you can look at it. But to be honest, it's kind of like over the top, and it won't be like some. It won't. It's not representative of the exam. Yes, that's a lot of parentheses. So I'll go to the reset of 2017. Can the entailment arguments be swapped? So what you're saying is, if there, no, you can't swap them, because if you swap the entailment arguments, so you're saying like if student X and attended both lectures, right? Then both of them. Is this what you're saying? Can the entailment arguments be swapped? Because if you swap them like this, then it doesn't make sense anymore. Because now what you're saying is, no, it doesn't make sense if you do it like this. It has to be this way, because if we look at it this way, now we're saying if a student attended X and if a student attended Y and Z, then Y and Z have to be lecturers. But that's not what the statement is saying, right? It's saying that if they are lecturers, then there is some student which attended both of them. So by what the question is saying, it doesn't work in both ways. Do you recommend to do the digital exam? So the thing is, I don't think you get to choose which grade you get. I think latest grade always counts. So if you have a decent midterm grade and you pass the digital exam, just keep your grade. If you pass the digital exam and you're not satisfied with your midterm grade, then yes, do the physical exam and see if you can up your grade. But otherwise, I think well, yeah, you okay, sure, you get the average, but then still, like, the average can also go down, right? It's like, so the thing is, with the digital exam, you get the opportunity to keep your midterm grade as your final grade, right? So if your final grade is low, then yes, you can pull it up by doing the final exam, but then it can also go the other way around, right? Where your grade may go down because of the final exam. Like, in my opinion, I thought the final exam was a bit harder than the midterm. And also, there's... Do you know when you will receive a pass? Well, I mean, it's just if you get a 5.5, then it's a pass. It's like just as with any other exam. Okay, right. Anyway, so I'll just continue. I'll pull up Reset 2017. Well, for the physical, you don't have to have a 5.5 or above, but the average needs to be 5.5 or above. So if you have a 4 for the midterm, then you need at least a 6 for the final. Right, so this is from the 2017 reset. It's a question on predicate logic. So it's 9 points, and I think these exams go until 100 points. So this is like quite a lot of points for a question. And so what it's saying is give a model consisting of two elements. So our model is AB, right? With brackets, nice. That shows the true two predicate logic formulas below are not equivalent. And well, it's super easy, so. If this is our model, CADB, then this holds for the first one, but it doesn't hold for the second one, right? Because the second one is saying for all x, they are all C, or for all x, they're all D. But here we have C and D, right? So it holds for the first one, but it doesn't hold for the second one. And that's literally everything you have to do. If you can show this, you get 9 points. But then give an explanation as well. Explain why this holds for the first one, but it does not hold for the second one, right? Okay. So this is a. What do you mean? Well, okay. How do you show it? So what you do is you write down. Okay. You say, okay, well, this is my model, CA and DB. So assume. Okay. Actually, let's write it down as text. Okay. Assume CA and DB. Then the first predicate holds, but the second one does not. Therefore, they are not equivalent. And that's your answer. Now you get 9 points. Yeah, that's it. Because the question is only asking to show that they are not equivalent. It doesn't ask for like entailment. You don't have to show entailment or anything like that. You just have to show, you have to give a model. Well, this is your model. You have to give a model, assume CA and DB, that's your model, consisting of two elements. Well, we only have A and B, right? So we only have two elements, and it shows that they are not equivalent. Well, it shows they are not equivalent because this one holds, but this one does not hold anymore. Most part of this question, and that's why it looks super, you're like, wow, okay, one sentence, I get my points. But most of the hard part of this question is understanding how these two are different, right? How can I create a model such that these two are different? Well, luckily, this question is super easy. It's super easy to come up with a model. The second one does not hold because we have CA and DB. And what the second one is saying, it's saying that for x, all x need to be C or all x need to be D. Okay? So it's saying, so the second one only holds if DA and CA or if CB and DB. The second one only holds if either of these two, right? For all x, they're C, or for all x, they're D. But then that's not the case here, right? Here we have two different elements. And that's why the second one does not hold for CA and DB. Yes? If we have a single element, let's say we have A, then it will always hold. Because if we say CA, the first one holds and the second one holds, and if we say DA, right, then the first one holds and the second one also holds. Yes. So yeah, you're right. And then on the final exam of 2018, there's also a bit more predicate logic. So I'll also pull up that one. And from what I can remember, that one's also very easy. So you can already see the predicate assignments on the exam are much easier than the ones we've discussed so far during, the working groups, which is usually the case. The questions on the exam are slightly easier. So question 8 of the 2018 exam. these are the unary predicates that we have, and we need to express the phrase every doll is in one of the two boxes. Okay? So we know that for all dolls, for all x, if x is a doll, well, then this implies that they're in the first box or they're in the second box. That's A. Does this make sense? Every doll is in one of the two boxes. Well, for all elements x, if x is a doll, then it's in box 1 or it's in box 2, right? And you can even write this with exclusive OR if you wish to, but writing it with just an OR is also fine. It's an implication because inside the box there may also be a ball, right? The implication is needed because we're saying that if it's a doll, well, then it must be in one of the boxes. But then it may be in the box if it's not a doll. We don't care. So that's when we need the implication. And so one good way of knowing when to use implication is if you can express the sentence with if then, right? So every doll is in one of the two boxes. You can rephrase this as if it's a doll, then it's in one of the two boxes. Yes, exactly. And so because you can rephrase it with if then, you know that you kind of need this implication. Also, no, wait, this is even a better tip I can give you. If we want to express for all x, okay, if we want to express for all x, we use implication. And if we wish to express for some x, we use and. Okay, so this is kind of a guideline that you can keep in mind because this applies in like 99% of cases. And I'll show you. It'll make sense. I'll show you. Right, so. So it makes sense because now let's say we say that there exists some x such that it's a doll and it's in the boxes, right? Well, then we get this. Now we're saying there exists a x which is a doll and it's in one of the two boxes. So now we get there exists with and instead of for all with implication. Okay? But then, well, that's not what the question was asking. But that's just to give you an idea of why it works and why you can be pretty sure about using it like that. So for B, we have all dolls are in the first box or all dolls are in the second box. Okay? Well, we know that for all x, can we use either or? Well, yeah, you can use exclusive or if you want here. You can use or you can use exclusive or. Both are valid answers. So for the second one, all dolls are in the first box. So for all x, if they are a doll, they are in box 1. Or for all x, if they are a doll, they're in box 2. Yeah, so that's why I'm saying you can use or you can use XOR for the first one, but it does not matter. And like similarly for the second one, you can use or you can use XOR here. It still does not matter. Yeah, it still does not matter. You can use both. The thing is, in like logic or predicate logic in general, we don't really use XOR that much. So even though XOR would be like, I guess, the perfect answer, just having OR is fine. I mean, no, but the thing is, with predicate logic is more closer to actual linguistics than it is to logic, right? So if I'm saying all those are in the first box or all those are in the second box, you know that the or I'm saying is an exclusive or, right? You know that logically they cannot exist in both boxes at the same time. So therefore, using just normal or is fine. I guess that's just a property of like, yeah. Well, yeah, I guess it's stupid that we're switching to linguistics now, but I mean that's just like predicate logic, okay? Then the main thing about predicate logic is reading and like understanding what it says, okay? So being able to read what this sentence says and conveying it as like a predicate, okay? So, but yeah, now you know, at least you won't have to forget. Yeah, it is being recorded in a sense that there's gonna be a VOD which you can just rewatch at a later time. It's going to be available for 14 days, but I'll probably remove it after the final exam. But then it should still be up until Thursday, I think. So anyway, C, are the formulas in A and B semantically equivalent? If so, argue they coincide on all models. If not, give a model on which they produce different truth values. And well, guess what? This is the exact same answer that we've given to like 3 questions already. So let's say we have 2 elements. We have element A and we have element B, right? And A is in box 1 and B is in box 2. Well, then the first one holds, but the second one doesn't hold anymore, right? And so that's a model in which they produce different truth values. And that's your answer to C. And well, you get 7 points for this, so that's really nice. Questions about this? If not, then I guess we'll move on to the exam from last year, which is the exam that I got the most questions about, which kind of makes sense because, I mean, this is the most relevant exam, right? So we have final 2019 and solutions 2019. So first things first, we have question 3, which is an OBDD again. And then we have question 4, which is predicate logic, questions 6 and 7. Okay, cool. Yeah. So you guys want to do the OBDD? If I don't see yeses, I'm just gonna skip the OBDD because... No, that's Russian. Okay, well, I'm gonna go over it quickly then. No, I won't skip it. We're gonna do the OBDD. Right, so we have a formula, not x or y and x or not z, by means of, and we have to represent this by means of a binary decision tree with respect to the variable ordering x, y, z, right? So, well, we're given the ordering. So since we're given the ordering, what you do is you just draw down the tree skeleton, I guess. Right, so this is what your tree gonna look like, right? And now we need to look at what the formula is saying. Well, the formula is saying if we have not x or y, so if we have not x or y, then the tree is gonna be true. No, wait, no, I'm lying. Wait. You can look at it this way. So if we have not x, then we can't have x, right? So if we have not x and we have not c, so we have not x and not c, then we're going to have a 1. Agree? Not x and not c gives us a 1. And if we have a y and not c, then we're also going to have a 1. And alternatively, I guess, if we have a x and a y, then we also have a 1. So everything else should be a 0. Yeah. Okay, well. Sometimes we lie. Thing is, I was lying, but I was not wrong. So anyway, this is like what the tree is going to look like. So, well, we're going to apply C1, right? Collapse the leaf nodes. Right, so these are both going to go to 1. This one's going to 1. This one's going to 1. And everything else is going to go to 0. Right. Well, we see that these two are both going to the same node, right? So we can remove them and just redirect their incoming node. So this one's going to go to 1. And this one's going to go to 0. And similarly, these two we can merge, right? And this looks an awful lot like a tree we've drawn before, actually. I'm pretty sure it's the exact same tree on one of the exercise sheets. And, well, as you can see, we can apply C2 again here, right? We can get rid of this one. So this is the reduced OBDD that we're left with. Yeah, do people understand this? Like, are there questions about how to get to this? Well, yeah, well, you need to show these steps in a sense that you're probably no, don't just show the final tree. Preferably show the step. I applied both, but the thing is, so the answer sheet for these OBDDs, right? The answer sheet for this exam is online, so you can just look at the exam sheet and see how they apply the intermediate steps and what names these steps have. So in a sense, like, you know, this exists already online, so you can just look at it, okay? But yeah, so this is the reduced OBDD, right? And so now the second part of the question is to construct, well, actually, so the first one was drawing the tree, and then the second one was applying the steps, right? So applying the steps, we get this here. And so now we have to construct an OBDD for this one here. And so we have to do it for all y. And so first we're going to draw y is 1. Well, if y is 1, then this one's going to go to a 1. So we have x going to z, going to 1. And then x true is just going to go to 1. And for y is 0, we're going to take this one here, right? So what we're going to do is we're going to draw it like this. And now this is going to go to 0, just as with the z here, right? Okay. So we've drawn y is 1 here, and we've drawn y is 0 here. And because it's for all y, we need to take the conjunction of these two, right? So we take the conjunction of these two graphs. So then, well, x is false gives us a z here, right? X is false gives us a z, and x is false gives us a z, and here x gives us a 0, and here x gives us a 1. So what does this mean? Well, we have a z here, and we have a 0 here, and we know that z, if it's true, goes to 0, and if it is false, it goes to 1. And so this is the tree for all y, the reduced OBDD. Well, so what I'm doing here is basically the O prime stuff. So yes, if you just do this like I do it here, that's the same as doing the whole O1 and O2 prime stuff. So, I mean, I don't really like writing down O1 and O2 and that kind of stuff. So I just write it down like this. And I mean, you still get the same final answer, so it's fine. It should be fine, okay? If it's not fine, you get points deducted for this, and it causes you to fail, then go to 1 and complain, and then he's gonna give you your points because he shouldn't deduct points for this. Okay? Should be fine if you just do this. Well, I mean, I get that you don't like it, but then I also don't have a definite answer, right? Because I don't make the exams, and in fact, I don't grade the exams this time because everything's gonna happen at one's place, right? So he's the only one gonna be grading everything. So then you're gonna have to send him an email and ask him what he thinks. Yeah, I'm sorry. So question 4 for the 2019 exam. It's a predicate question. And the first thing we need to do is we need to give a model that shows that they are not semantically equivalent, right? So usually when you have to give a model, well, it's best to have as less elements as possible, right? And so 2 elements usually works. So we'll use elements A and B, and now we're going to try to find a model that shows that they are not semantically equivalent. Well, the first formula is saying that there exists a y, okay, there exists a y such that all x, such that for all x, x relates to y. Okay? So that's basically what the first formula is saying. And there may be another y here which does not have any incoming errors. It doesn't matter. It says for one y, there exists a y such that all x relate to it. Okay? The second formula is saying that for all x, there is a y such that x relates to y. So for all x, there is a y that they relate to, but it doesn't have to be the same one, right? And so clearly you can see that, well, these models, they look different already, right? And you can see that this model, right? If this is our model, then this holds for both, right? But if this is our model, it holds for the second one, but it does not hold for the first one. And so this should already tell you a bit that the first one, so formula 1, semantically entails formula 2, right? If formula 1 is true, right? If this one is true, then this one will also be true by default. Does that make sense? So you can show that they are not semantically equivalent by... wait, no, that was wrong actually. I shouldn't have removed that one. But you can have element A and you can have element B, right? And you can have it such that let's see. For all x, there is a y that they relate to. Yeah, no. Personally, this model here is what I would draw on the exam. Because this makes most sense to me. Because if you draw your model like this, then the second one holds, but the first one doesn't hold anymore. And then what it says on the answer sheet is like, yeah, we take elements A, B, and we create relationships AA and relationship BB, right? And then the second one holds, but the first one does not hold. So I guess you could do it like this as well. But I like to do it this way because visually it works better and it achieves the same goal, right? But so yeah, if you give this as a model or if you give this as a model, both of them are valid, and then you just show that F1 semantically entails F2, aka if F1 is true, F2 will always be true, but not the other way around. So we also have question 6 from the 2019 exam, which is compositions. Again. So for each of the functions, determine whether or not the function is injective. Please give a brief explanation of your answer in each case. Okay. So the question is if square root is injective. Well, square root is not injective, right? Because for square root, you know, let's say we take the square root of 2. Oh wait, it's like wait, it's the squared. Sorry. These both give us 4, right? So therefore, because there's 2 inputs that give us the same output, it's not injective. This function here, x minus 1, this is injective, right? Because for each input, there's only going to be one output. And for each output, there's only going to be one input that we can give to get there, right? And finally, inverse is also injective, right? Because for every x that we give, we get a unique output. And by just explaining this, it should be fine. Because they just ask for a brief explanation. And then we have to give an explicit description of f defined by this here. Well, shouldn't be too hard, right? We know f x. So first we do this, x minus 1. Then the inverse of the square, which is a root. And then we inverse this, so this is divided by x. Does that make sense? No, wait. It's 1 over this thing. So we have 1 over this. Yes. No, square root. Yeah, exactly. They're only. So this one is not injective, but these two are injective. Well, the square root is not injective because this gives us 4. This also gives us 4, right? And so we have multiple inputs which give us the same output, which goes against the definition of injectivity. Right, cool, amazing. And so for b, we end up with this here, right? 1 over the square root of x minus 1. Right, so injective means, so we have a domain and we have a codomain, right? With injectiveness, for every input, we have exactly one output, right? So it can't be the case that 2 inputs have the same output, which is the case with the square root, right? We have input 1, right? Input 1 from the codomain, and we have input 2 from the codomain. And, well, they go to the same output in this one here. You can't have one input and 2 outputs. If you have one input and 2 outputs, you don't have a function. One input always has one output. Yeah, exactly. It won't be a function. What do you mean, the square root? The square root only has one output. So surjectiveness means that if you have a domain and you have a codomain, it means that all values in your codomain can be reached by some value in your domain here. So let's say that in your codomain you have 1 and 2. It means that for all values inside your domain, you can reach 1 or 2. So that's surjectiveness. It means you can cover your whole codomain. Any value that's in here, we can get with some input. Yeah. So then finally we have to express the function g r to r defined by the description here, and we have to write it as a composition of the functions, these ones, and their inverses, right? Well, first of all, we see the square root here, right? Then we have 1 plus x over x. So I think then what we get is inverse. Does that make sense? No, it does not make sense. I think, yeah, so then what we're left with, so after doing the square root, right, we're left with this here, right? But that's the same as 1 plus x over x, I think. 1 over x plus x over x, yes. And so that's why you do this first. Oh, no, don't want colors. And then finally you do the inverse, right? Yeah, and so that's this function here. And that's question 6, yes. And then finally we end up at induction again. So this is induction from last year, right? This is from the exam from last year. And this cost me 10 points. And I actually wrote this down because I know otherwise I'll mess it up. Okay, so we have to verify by explicit calculation that the statement is true for n is 1, n is 2, and n is 3, right? So, I mean, well, that's not the hardest part, right? So that's just plugging in the numbers. So if n is 1, then we have 3 times 1, which is 1 minus 1, right? Which is 3 times 0, 0, right? And so that's the same as 1 times 1 squared minus 1, which is 1 times 0, 0, right? So for n is 1, this holds. Now, for n is 2, 3 times 2, 2 minus 1, gives us 6 times 1 is 6. And similarly, we have 2 times 3 is 6, right? So for n2, it also works. It's very easy. Well, for n is 3, we have 3 times 3. Or actually, as a matter of fact, so if n is 3, then that's 0 plus. So that's the same as saying n1 plus n2 plus n3, right? Because it's a summation. So that's 0 plus 6 plus 3 times 3, 3 minus 1, right? So that's 6 plus 9 times 2, 6 plus 18, it's 24. Yeah, so no, you have to write down the sum, so that's why I added here. For the second step, it didn't matter because n1 is 0, right? So we were adding nothing. But yeah, you're right. Anyway, so n3 we get 24, and well, we can confirm if that's correct. 3 times 3 squared minus 1. Well, that's 3 times 8, which in fact is 24. Okay? And so we've proven that it holds for all n 1, 2, 3. So now we have to use mathematical induction to prove that the statement is true for all integers bigger or equal than 1. So, well, base case, n is 1. We've proven that n is 1 holds, right? That's what we've done here. So we don't have to do that one anymore. So base case is proven. So now we assume some m bigger than or equal to 1, right? So then what we get is the sum of k is 1 of m is 3k, k minus 1. Okay? So we know that for some m, we get this. Now, if we want to find the sum of k is 1 for m plus 1, well, that's the same as saying this thing plus m plus 1, right? So then what we get is m minus 1 plus 3 times m plus 1 times m plus 1 minus 1. We just take this, we substitute m plus 1 in here. In my equation or in their equation? Oh yeah, so this is an m. Yeah, hey, you're right, thank you. Okay, so, but this still makes sense, right? So we know that the summation for our formula gives us this, right? Now we want to show m plus 1. So since this is m, we need to do m plus 1, right? Which is just plugging in m plus 1 into the k part, right? So this part here, that's this. Okay? And so we end up with this big thing here. So, well, now we can try to rewrite this. So that's m. This is still an m. Yes. So that gives us m to the third minus m plus 3m plus 3 times m plus 1 minus 1 these cancel out, by the way. So that's plus 3m squared plus 3m. And so this gives us m to the third plus 3m squared plus 2m. Okay? And so now what we can also do is we can take this one here and now what if we substitute m for m plus 1? Well, what we get is we get m plus 1 times m squared plus 2m plus 1 minus 1, right? And so that's going to give us m to the third plus 2m squared plus m plus m squared plus 2m. Does that make sense? 1, 2, 3, wait, that's one term too many. So m times m squared gives us m third, m times 2m gives us 2m squared plus m squared plus 2m. And so this is m to the third plus 3m squared plus 2m. And well, that's exactly this. And therefore we have proven that the statement is true for all integers bigger or equal than 1. Yes, I hope that's clear. Yeah, if that was clear, then this is basically everything from the Google Doc sheet. So unless there's specific questions, that you still want to have covered, I think that's it. So yeah, I'll just wait around. Can you, from the first equation, can't you? Well, the thing is, you can substitute m plus 1 directly into here and end up with this here, right? But then you have not really shown that the induction works, right? Like, so the thing is, with induction, you have to show this side and you have to show this side. Well, showing this side is easy, right? It's just plugging in m plus 1. But how do you show that this side also holds still? Well, the way you show that this side holds is by doing all this. Right? So if you show that both, can you redo the first part of B again? Okay, yeah, sure. So I'll remove this because we already know that it holds for the second half, right? So this is really not that relevant anymore. But I'll go through the first part. So, like, this part here is just simplifying, right? So it's like this part that's relevant. Right. So we know that this part here, it's a summation, right? This part is a summation. So So let's say m. This is just like k is 1 all the way to k is m, right? And so everything k1 until k of m we can summarize as this part here. So that's m squared minus 1. This is equal to everything up until k is m. But now we want to show that, instead of k being m, we want k to be m plus 1, right? And so we know that at the m plus 1th step, right, we're going to substitute k for m plus 1. So we have 3m plus 1 times m plus 1 minus 1, right? That's the m plus 1th step in the summation, right? So that's where k is m plus 1. And so because we still have k is m here, right? So the summation now because if we want the summation where k is 1 all the way to k is m plus 1, then still this part here is k until k is m, right? And then here we have m plus 1. And so these two are the same. And so that's why we can take this part, right, to cover this. But then we still need the k plus 1. K is m plus 1, which is like this ugly thing. 3m plus 1, m plus 1 minus 1, right? And so that's why you get this big ass formula, which is what I wrote down here. And you simplify this. Yes. It's convoluted, but practice makes perfect. So just try it a few times until it makes sense. So other questions, like specific stuff? If OBDD leaves are incorrect, but it is reduced correctly, will you give marks for the correct reducing? Well, first of all, I still can't say because I'm not going to be grading. Only the teacher is going to be grading. I think that if your leaves are wrong, then your tree is also going to be wrong. So that's going to be really bad for you. So yeah. Don't make sure the leaves are correct because otherwise your whole tree is going to be incorrect. All right, so I'm just gonna assume there's no more questions. If there are still questions, well, your exam is on Thursday, right? So you still have 2 days. I'm pretty sure you can email all of the TAs about specific questions. You can also ask to have a specific question covered. Yeah, no, we're not gonna do this. Whatever you're gonna draw. Right, so yeah, you can have like if there's a specific question that you don't understand, you can still like send an email about it, and maybe a TA will just like reply back to you with like the full answer, something like that. And obviously this FOD is gonna be online, so you can just rewatch it if there's specific stuff that you don't understand. Other than that, yeah, I mean, the Google spreadsheet is still here, right? So these are the things we covered today. And these are also all the important topics that you really should know for the exam, I guess, in the end. If you know how to do the 2019 exam, you should be fine. You should be completely fine. Especially because this is online, so you do have some leniency in a sense that you can look up stuff, right? So, but then I mean, I didn't say anything about. Bro, I think nobody's doing good with the corona stuff. All right, no, I'm not hosting anyone. I'm just gonna go. Yeah, rewatch the VOD if you have questions, or send me an email, or whatever other measures. And I guess thank you for coming. So, good luck with your exam. Bye bye.